start. I mean, right, good morning. So let's just start from the last week's class. So what did we say? We said that quantum mechanics necessitates the formulation in terms of linear vector space. And Dirac was the proponent, but there were others who also played significant role. Newman, for example, Schwartz, for example, these guys also played the important role. From one thing which I can tell you pretty quickly, you have gone through your Schrodinger equations, but people do not do, for example, Heisenberg matrix mechanics, which was developed at the same time when Schrodinger's equation was getting developed. So the two different formalism looked very different to begin with, but it was Dirac and the formalism which he presented in terms of linear vector spaces that he managed to show that both of them are equivalent. Anyway, what can we think about this linear vector space? This linear vector space in one sense is the extension of three-dimensional Euclidean space, the vectors which we write. And we are relaxing the dimensions, so no longer talking about 3 dimensions, and relaxing the word real. So as we know that this three-dimensional vector space is a real vector space. And how did I define it? Since it's a new algebraic structure, so we'll have to give some structure to it. So we define it as a triplet such that we call V as a vector field, vector space over a field F. This field can be real or complex, such that it has the definite rules of vector addition and scalar multiplication. So we need two things. One is vectors, and we also need scalars. So vectors are over the vector space, scalars are over the field. But in order to define the linear vector space, we have to have these three things defined. The reason for using this interesting sign, this plus and then encircling it, it is just to tell you that what we are talking about is vector addition, and I am going to show you with certain examples. Fine. Then the notation which I am using to denote vectors is something what we call as the Dirac cat, and you will be using it in your quantum mechanics class as well. In mathematics, it's common to write down whenever operations are defined, like plus, vector addition and scalar multiplication, that what does that application do? So the last line is about what does that application do. So if you take one vector and add to it another vector, then the corresponding result will be the vector in the same vector space. So it will not go out of it. It will remain in the same vector space. Remember it from the three-dimensional vector. Addition of two three-dimensional vectors, it will be still another vector. And the scalar multiplication, if you multiply a vector by a scalar, then it will again be a vector. So these are the two famous closure properties. But we did not only do the closure properties, we also did all the 10 properties. And those are the ones which I listed last time, that in order for any triplet is vector over a field along with vector addition and scalar multiplication. In order for a vector space to be called a vector space, each of the vector will have to follow these properties. So that if we are taking two vectors, then it is still in the vector space. Associative, existence of zero or the null vector, existence of the inverse, commutative property, multiplication by a scalar is still the closure property. Then we see that alpha plus beta, if you are going to do multiplication with that, it is still so distributive properties of the vector space. Finally, that there exists a scalar 1 such that if you multiply 1 with this vector, then you are still getting a vector. So this is what we did. Today my plan is to give you certain examples. Then we talk about the few properties and subspaces and linear independence. So let's just see how we go further. Now, the easiest and the simplest example which I wanted to give is of three-dimensional. So let's just say first example, vectors, 3D vectors. So how did we define 3D vectors? Let's say, let me define x1i plus x2j plus x3k. Remember, this is the way you used to define it, right? So Sometimes you also call it as a collection of x1, x2, and x3 for a given basis. I'm going to talk about that. But each of these xi, they belong to real number space. So not talking about the complex space. Remember the three-dimensional vectors. Yeah. Now the question, whether the three-dimensional vectors form a linear vectored space or not. So what are we supposed to do? We are supposed to see if these vectors follow all the 10 properties which are written on the previous page. So let's just see. First of all, the closure property. So if I have another vector, let's say y1 plus y2j plus y3k, and since you know the vector addition rules, so what will be the resultant of r1 plus r2 vectors?
x1 plus x2 y1 plus y2.
x1 plus
Yes, sir, it will
y1.
be vector.
So yeah, I mean, you are going to say that, but I still want to say what I want to. Good that you already know it. The important point to note, each of these xi's are in real number space. The question is, when you add the two vectors, are the coefficients which you are seeing, they belong to the real number space or not? Whether the addition of two real number is a real number or not?
Yes.
And we'll,
Yes,
yes, it
sir.
is, and hence we will.
Sure.
Yes, sir.
Right. So addition is a vector. It is still remains in the same three-dimensional vector space. Okay. What about multiplication with scalar? So let's say alpha is any real number. So alpha is any real number. And if I multiply my vector with this, so what will be the result? Alpha x1i plus alpha x2j plus alpha x3k. Now question, does each of these component multiplication of the two real numbers, is it a real number?
Yes.
Yes,
Yes,
sir.
Yes.
sir.
Yes. So that
Yes, sir.
means that this also belongs to the same three-dimensional vector space. Now, is there any zero vector? Do you know of such that when I
Yes, sir.
add this vector, it should still be the same. So what will be the zero vector?
0 I plus 0
0 I
0.
plus 0
0 y, absolutely right.
Zero.
So component 0, 0, 0, that will be called as the zero vector, right? What about the inverse vector?
Yes, sir. The negative of everything.
My negative of
Negative
that.
of this, very good. So this will have minus x1, minus x2, minus x3. This will constitute my inverse. And you can see the rest of the properties will also be valid. So what happens that this three-dimensional vector space basically constitutes a vector space. So we can call this three-dimensional vector space a linear vector space. And what kind of linear vector space? Since my scalars are all real, so it should be a real 3D vector space. So what we call as the three-dimensional 3D vectors, they fall under this category. Yes. But what we are doing is the generalization. So let me show you how we are doing the generalization. So let me do example number 2. Let's talk about a space which I am defining as R and R. So this is my field, which is field of real numbers. R is the, and Rn, how am I defining it? I define it as, let's say, just like your 3D, I am just extending it to n such numbers. So x1, x2, x3 up to xn. So each of this xi is nothing but R, belongs to R. So what I mean, in one sense, you can see that this is just the extension of three-dimensional vector space. I am taking it to n numbers, collection of n numbers. Yeah. So let's say this is my vector number 1, and I have another vector y1, y2 in the same space, such that of course each of this y belongs to R. Question: if I define the rule of u1 plus u2, so I have to of course define the rule. So which is nothing but component wise addition, just like the way you were doing in three-dimensional vector. And I define my scalar multiplication, which is each component multiplied by alpha. So first question, will the addition of two such vectors be a vector or not? So u1 plus u2, since the rule is defined, this will be x1 plus y1, x2 plus y2. It is one way you are basically extending your three-dimensional space. Now, does each of the addition is still keeping you in the real space, or it is taking me out of this?
Yes, sir.
It's
Yes,
taking
sir.
it's keeping
Yes,
us in the
it's in
same
real
space.
space, sir.
So
It's in
that
real space.
the closure property is met. What about this? So alpha x1, alpha x2 multiplication. Again, I mean, basically simply extending the concept. Will this be again in the real space?
Yes, sir.
All the numbers?
Yes, sir.
Yes, sir.
Because
Yes,
we are
sir.
multiplying. We have
Yes,
already seen it.
sir.
Very good.
Sir.
So we see this. We can again think about the zero vector where all of these numbers are zeros, right? We can again think about the inverse vector where all of these numbers are minus x1, minus x2, minus xn. We can again see the distributive, the associative properties, and we will see that just like R cube R, the three-dimensional vector space, this Rn R also constitutes a vector, linear vector space. Okay, so we have just seen that linear vector space is a concept which allows me to extend my three-dimensional vector space. Let's just continue and do few more examples to understand it further. Okay, let me give you a simpler version. I have a set of vectors where I have only two numbers and each of this number is a real number. Fine. So I define my u1 as collection of two numbers, and I define my u2 again the collection of two numbers, both of which are real. Just y2, and it is still defined exactly in the manner in which we were doing. So now see why I am writing plus and then circle it, because the rule of addition which I am giving to you is that u1 plus u2, the two vectors, are going to give me x1 plus y1 for the first component and x2 minus y2 for the second component. Yeah, each of these is still a real number, so that's not an issue. Now, question, does this set correspond to a linear vector space over real numbers? Does this set? Okay, yeah, keep your pen and paper ready and help me out.
Sir, I don't think it will satisfy the distributive or associative properties.
Yeah, actually, you know, don't even need to go there. Let's just do a simpler one. u2 plus u1, which is what? This will be, help me writing down that. u2 plus u1. The rules are
Y1
given
plus
here.
X1
y1
Y1
plus
minus
plus
x1. Thank you.
plus
X1
X1
Y2 plus.
comma
y2
Y2
minus
minus
x2.
X2.
minus X2.
That
Right
doesn't
now,
even satisfy the
question.
commutative.
Right. Question. The linear vector space has to have the commutative property, which means u1 plus u2 has to be equal to u2 plus u1. Are these same?
No.
x2 minus y2?
No.
No, sir.
No, sir.
No, sir.
No, sir.
No, sir.
That means this set is not a linear vector space over real numbers. So, in order to ensure that we understand if particular set is obeying this real number, I mean linear vector space or not, it has to meet all 10 properties. Of course, you can see other properties also, yeah, just like the way you are saying, maybe the associative properties and the distributive properties. These may also fail.
Hello, sir.
Yes.
Sir, can you explain ये x2 minus y2 minus कैसे हुआ?
Oh, this is what I was telling you that ये मेरे rule है इस मैंने आपको एक set दिया and the rule of this set is such that when the two vectors add then this kind of results will it will result in this kind of combination x1 plus y1 and x2 minus y2 ये हुआ नहीं. Remember that I told you that there has to be rule for the vector addition. This is the rule for the vector addition which I am giving you. It is not, it is there. And I am asking you whether if such a rule exists along with another product rule, will such a set constitute a vector space or not? And you will say, sir, with
Okay,
this
sir.
rule, this is not going to constitute a linear vector space.
Linear vector space. Yes, sir. Okay.
Right. So this is the rule which I am giving you. The reason why I am giving you this rule, just to tell you that this plus can be anything. So in future, I will start writing my plus as simply like this because we get habitual to adding the vectors. But please understand the importance that we have to define the rule of vector addition. Unless the rule of the vector addition and the rule of scalar multiplication not defined, we cannot proceed further. If nothing is given to you, then it is assumed that we are talking about the rules which are the normal rules. The normal rules are the way we are defining our previous one. Let's just proceed further. Good question, by the way, that from where that rule came. So let's just think about 2 cross 2 matrices. And I call it, let's say, M2 cross 2. And I am going to put it over a complex number space now. Fine. So let's just say A, B, C, D as a general matrix, 2 by 2 matrix, right? And where each of these A, B, C, D can be a complex number. Okay. And of course, I can define my U2, P, Q, R, S, which still belongs to the same. Each of these P, Q, R, S is a complex number. So let's define the rule for the matrix addition in this space. So rule of the addition is the regular matrix addition. How do we do the regular matrix addition? Or the usual matrix addition? If I have to add two matrices?
Component-wise addition.
Component-wise addition. And what about the multiplication by scalar?
Multiplying the row with the
Component-wise
Component has to be
multiplied
multiplied by the
each
scale.
component by.
Each component multiplied by that scalar, right? So now tell me whether this thing under this field where alpha, beta, gamma, they all belongs to a complex space, whether this will constitute a linear vector space. So regular matrix addition and scalar multiplication.
No, sir.
Okay, so which property will it fail?
The commutative under multiplication.
Multiplication, sir.
Yeah, but I am not giving that multiplication rule. I am giving only matrix addition rule. Remember what we are supposed to do? So this is M2 cross 2. Let me just write it for your convenience. My rule for vector addition is just the addition of the matrix, which is matrix addition. And my rule for scalar multiplication, let me just write down U1 plus U2. What will be that?
A plus P.
A plus
A plus P,
A plus P,
P plus
B
Q,
plus Q,
P plus R,
P plus
P
R,
plus
D plus
S.
S.
This is still a 2 by 2 matrix, right? Each
Yes,
of these, is it a complex number or not? Each of the component?
Yes, sir.
Yes, sir.
Yes,
So
sir.
complex number is a complex number. So this belongs to my same vector space, right?
Yes, sir.
And you
Yes,
can do
sir.
all the properties, I mean, commutative, associative. Just a sec. Alpha U1 will be what? Alpha times A, alpha times B, alpha times C, alpha times D. Multiplication of a complex number with a complex number. Is it still going to be a complex number?
Yes, sir.
No, sir.
Yes, sir.
Yes.
Yes, sir.
No, sir.
Complex number multiply.
No,
Multiplication of a
sir.
complex number with
No, sir.
complex number.
It will be.
So
Not. It will be.
Yes, sir.
number.
Complex
Not
number.
all time.
It will be complex.
अरे भाई ये तो बता दो आप मुझे,
डिपेंड करेगा ना
सर
सर।
कॉम्प्लेक्स होगा।
क्या डिपेंड करेगा?
सर होगा कॉम्प्लेक्स
सर
होगा।
कॉम्प्लेक्स ही होगा, डिपेंड नहीं करेगा।
सर
कॉन्जुगेट
कॉम्प्लेक्स
होगा कि
होगा।
नहीं होगा?
अरे भाई कंजुगेट
वो
नहीं भी
फिर तो
होगा तब भी
कॉम्प्लेक्स हो
क्या?
गया ना।
सो लेट मी जस्ट गिव यू समथिंग, अल्फा आर प्लस आई अल्फा इमेजिनरी and beta r plus I beta imaginary. Will this be a complex number or not?
It will be.
कॉम्प्लेक्स
Yes,
नंबर
It
सर।
will
yes,
always
sir.
Yes,
be,
sir, it
no?
will
Yes,
be.
sir, it will
Yes,
be
sir,
complex.
always.
It will always be a complex number. Multiplication of two complex number is a complex number, and that is why complex number constitute a field, which I am not going to do further. But this is also a vector. This will also exist in the same vector space, and you will see that under this rule of matrix addition and scalar multiplication, it will constitute a vector space. If I change my rule, of course, if I change my rule of this vector addition to the usual matrix multiplication, then it is not going to be a linear vector space. But under this plus rule, it is going to be a linear vector space. So matrices, square matrices of this form, they constitute linear vector space. In fact, you can generalize it to say that any n cross p matrices with complex coefficients defined over a complex field will always constitute a linear vector space under matrix addition and scalar multiplication, under usual ones. It is always going to. The reason for showing the matrices, that I am trying to tell you that the linear vector space does not need to limit itself with only n tuple of numbers. We can extend it to this one. Let's just take it to another one. Okay.
So, but then we have to define multiplication in this specific way that we can only allow
We are
scalar
not defining
multiplication.
multiplication. We are not defining multiplication. Remember, there is no need to define multiplication at this point of time. Do I need to? Because algebraic structure requires me to define only the vector addition and scalar multiplication. There is nothing else to be defined. What you are trying to think of, let me just tell you. What you are trying to think of, sir, I have read matrices. I have understood how the matrices add. I also understood how the matrices multiply. Matrix multiplication is AB is not necessarily equal to BA, which is not commutative, basically, you're saying. But those are the rules of the matrix multiplication which you have learned. Right now, for the vector addition or for the linear vector space, I do not need to think about it. I need to think only about this matrix space under the rule of matrix addition and scalar multiplication. I'm not saying anything beyond that. Yes, I have defined the standard matrix addition rule. I can again define some other rules. It won't be, it may not satisfy. But this particular one is surely satisfying, right? You will agree with that.
Yeah, yes, sir.
Okay, good. Let
Excuse
me
me,
just
sir.
take it further. Yeah, please go ahead.
So it's just a random question. In the last question, the dash is in the end edges of V. Does it have a different significance?
This one?
No, sir, the last question which you're telling, the dash at the end of V, capital V, does it have a different significance?
I somehow I'm missing this question. Can you just repeat this question? I elaborate.
Sir, actually, you are writing that it belongs to capital V. So
Aha,
you are
right.
you are writing, matlab you are making edges dash at the edges of capital V. Does it have a different significance,
This
or
guy
it's
or
just random? This one, V, capital V.
oh, I mean, see, since I am also writing my linear vectors, I mean, sorry, vectors as this, so I just put something like this to say that it is a vector space. Remember the notation which I mean, it has
Okay,
nothing
sir.
beyond that, right?
Okay,
Okay,
thank you,
got the
sir.
question. Yeah, there is no more significance that this still belongs to the same place, same space or same set. Okay, good. So one more last one I would take, and then of course, I mean, there can be plenty of these things which can be worked out. So let's see the collections of polynomials of degree n. So where I am defining my first vector as, so it's a collection of polynomials. How do I write a polynomial? So let's say P and T. How do I write a polynomial? So if
So
I, yeah,
different powers of T
X,
will have
x
some
Powers
square,
of
property.
yes. Some constant must multiplied by
Alpha,
extraordinary.
maybe instead of alpha, let me use a so that it will be easy. A naught plus, let's say, a1t plus a2t square plus so on and so forth, a n t n. So what is the degree?
N.
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 So in this case, we have degree n, and how many coefficients are there?
N plus
N.
1.
N
N plus 1.
N plus
N
1.
N plus
So
one.
each of these AIs can be real or complex. Actually, it doesn't matter for this question, but you will be able to understand my gist after I go through it. Let's say another polynomial, and that I define as b naught b1t plus b2t square, and I define my rule of vector addition as, so Pn plus Qt, a component wise addition, a1 plus b1t plus so on and so forth, an plus bn tn, and my rule of multiplication alpha a naught plus alpha a1t so on and so forth, alpha an tn. And now I ask a question: do the space of P and T with fixed degree n constitute a linear vector space or not?
Sir, fixed degree means that both of them will have same degree, right?
For not
U1 and
both
U2.
of them, all the vectors in this vector space have to have this degree. Remember, when I'm saying fixed degree, just like in the previous case, 2 by 2 matrices, all the matrices which should be there in that vector space has to have 2 by 2, right? So when I'm saying with fixed degree n, I'm talking about when I'm going to add the two polynomials, it should still be a fixed degree. It should not change in the degree. So fixed
Okay,
degree
sir,
is
got it.
all the polynomials in this vector space have to have degree n. Will this with fixed degree constitute a linear vector space?
No, sir.
No, sir. No,
Yes,
sir.
No,
sir.
sir.
No,
And why it
because
is no?
multiplying would,
So if
Sir,
alpha
because
equals to zero,
multiplying
n
would
is equals to minus
introduce higher
multiplication
powers
multiplication
of
if
is zero
alpha equals to
n.
0,
Right. So not only that is alpha is equal to 0. Yes, you are right. If I am multiplying 0 by a number, this coefficient will go to 0. Or you can say I can have the coefficients an and bn such that I have this coefficient 0 for tn, just like the same way you are saying. And in that case, my degree n will not be preserved. So collection of polynomials under the usual addition and multiplication with the scalar with fixed degree n does not constitute. Now let me just change the question. Will P and T with degree less than equal to n constitute a linear vector space?
yes, sir.
yes,
No.
sir.
Yes, sir.
Usual.
Yes,
So
sir.
this
Sir,
is
it will be.
no, and this guy will be yes, because now it does not matter. First, it is component wise. I mean, remember, it's the coefficients addition of the real numbers or the complex numbers, which will always be a real number or the complex number, as the case would be, and same for the multiplication. So it does not, and it does not matter whether some of the coefficients will be zero now, because I am talking about all the polynomials with degree less than equal to n. So all the polynomials with degree less than equal to n constitute linear vector space. In fact, it can be shown that all the functions, complex or real, all the functions, continuous functions, complex or real, they under the usual rule of addition, which is, so if I add the two functions, it is this. I multiply the function by a scalar, it is this. Then that all the functions of the real or the complex variables also constitute linear vector space. The square integrable functions, they constitute the linear vector
Excuse me, sir.
spaces. Yes.
Can
Say.
you please explain that the polynomial with degree less than n will form a linear vector space?
Yeah, I mean, the question is in the last case when we were doing in the fixed degree, the only problem we face that there can be certain coefficients which can add up to give zero coefficient for t raised to power n, and hence it cannot be the fixed degree. But for degree less than equal to n, there is no such issue, because if you are going to do this addition or multiplication by this scalar, it will always be a polynomial, whether maybe with some less degree or maybe with the exactly the same degree. So it is going to make it right. I mean, you follow all the 10 rules. You follow, this is the question. Basically, I cannot do all the time the examples, but you follow all the 10 rules and see if it is failing any one rule or not. Yeah. In fact, it can be seen that even the solution of the form of the equation like y dot d square y over dt square plus omega square y equal to 0. If we just take the solutions of the differential equation, then they also of this kind, that will also constitute linear vector space. So what am I trying to tell you? What I am trying to tell you that linear vector space is a concept which generalizes the idea of the three-dimensional vector space and is no longer limited to only n tuple of numbers. We can take it to matrices, we can take it to polynomials, we can take it to functions, differential equations, so on and so forth. So such an algebraic structure becomes very, very useful. And this algebraic structure is what we are defining as the linear vector space. One point, it has to match all the 10 properties. And in case if you are not clear about the vector addition or the scalar multiplication rule, be very clear whether you understand it or not. If nothing is there, then you assume the usual one. If something is written there, then you have to consider that rule and then check whether that particular rule is giving you a linear vector space. Okay, the second thing which I wanted to, with these examples, I wanted to tell you about, we call certain vector spaces the real vector space or real linear vector space, which I have told you, which basically is the field of scalars. If the scalars which what we are talking about are real, so if the field of scalars that belong only to a real space, we call it a real vector space, and correspondingly complex vector space or complex linear vector space is nothing but where the field belongs to complex numbers. So can anybody tell me whether quantum mechanics belongs to real linear vector space or complex linear vector space?
Complex.
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 Right. Remember, this is something which we try to think of, where C1 and C2 are two coefficients, which results in the linear superposition of the non-relativistic Schrodinger equation. Remember, and we told that multiplied by C1, which was the complex coefficient. So it is quantum mechanics belongs to this complex vector spaces. Good. Now let's just do some properties, few properties. So I said that 0, so properties, let's just write down. Vector is unique. How do we know that this is unique? We have to do it from first principles, that this is a unique. So how to go ahead with it? So there are certain rules which I already defined, which were 10 in number. And now we should be able to show from those rules whether what we are saying that this zero vector has to be unique and hence this nomenclature 0. So let's just see whether we can show it or not. So we propose that there exist two vectors which are 0. So there is no one vector but two. One is 0, one is O and another is O prime. So what is the definition of this null vector? Remind me. What is the definition?
The vector addition gives the same vector.
So this gives me same vector. Is it for one particular U or for any U which belongs to this vector space?
Any user.
Anyone, right? So now that we said that there exists the second one also, so that means there has to be another one, right? For all.
Yes, sir.
So that means this U, the 0, 0 prime, they all belong to the vector space. Yeah. So let's just see if the first one is same for all, is true for all vectors, and the second one is true for all vectors. In the first, Let's put u, just take this to be 0 prime. Since it is true for all the vectors, so let's just say that there exists this 0 prime. For that, it also has to be true. So let's just do that. So what will be the result? Just apply, put it in 1. So instead of u, I put 0 prime or o prime, whatever you call. This will be equal to
0 prime.
okay. And put in the second case. So that means instead of u, I put o plus o prime is equal to what?
0 vector.
Oh.
0 vector.
0.
Now look at the left hand side LHS. Now look at these. So o prime plus o, and in this case o plus o prime. So what happens to these two? Are they identical or not?
Identical.
Yes.
As per the definition of the linear vector space, vector addition is commutative, which means the LHS is same, and that implies that the RHS should be same.
Same.
Right? Which means that any O prime which we are talking about is nothing but this one. So there exists one and exactly one 0 vector. There has to be one vector which is a 0 vector, and it can only be one. Similarly, you can actually try to see if the inverse, that also I defined as unique. So please try to do it as a homework and see if you are able to do this. So these guys are the properties which we are basically getting from the basic principles. Those are the 10 rules. Now there are certain other properties. I'm not going to derive it, but let me just tell you, and those are obvious actually if you think about it. So if I multiply, for example, a scalar with any vector, then what should be the result? Whether it has to be a vector or whether it will be a scalar. So this is a scalar.
It's a vector.
The
Zero
vector.
vector.
So this will be 0 vector. It has to be proven, but this is right. Okay. What about this? If I multiply any alpha with this null vector,
It is also
We get
zero
0
vector.
vector.
0 vector. Okay, because of this guy, several books actually writes 0 as a vector itself. They do not even put a symbol like this. There is another reason which I will tell you later when you will be doing some advanced quantum mechanics, but they just put 0 as a vector directly like this. It is not notation, not beyond that. It is a vector, just like the way we are saying, but some books just write 0 as a vector. But we will continue to write this kind of a vector so that we understand whenever we are writing a vector, it can be polynomial, it can be a matrix, it can be n tuple of numbers or anything else. Okay, let's just give you some other properties and see if you can say that -1 take product with a vector u. What will be the result?
Negative of the initial
Inverse
vector.
Which
Inverse
is
of
this?
Initial vector.
Inverse, right? What about -1 of minus u vector?
It will give the inverse of inverse of u. So just
It's a
u.
Which
vector.
will
So
It will be just
U
U
vector.
vector.
right.
U
But
vector.
please see that all these should be proved from your first principles. That means from those 10 rules which we gave. Even though they are obvious and you should be knowing those, but it is generally just like the way I tried to prove the first one, the existence of a unique null vector. Similarly, each one of this can be proved. Okay, one very important property. Let me write down and then ask. If u plus v is equal to u plus w, and you are seeing that when I am using plus sign, it is basically this plus. It's the vector addition I'm talking about. If u plus v is equal to u plus w, what can you conclude about this statement?
V is equal to
V
w.
V equals to
V
W.
is equal to
V is
W.
equal to W.
This is the famous cancellation property. I'm not going to derive it, but please remember that. These are the interesting properties which come out of the linear vector space. I mean, those are regular ones, but yeah, it is still good to know. Okay, something extending it
Sir,
called subspaces. Yes.
sir, I'm getting some network issues. Please for the second property.
previous.
What was second property?
Oh, second, unique inverse. So
Okay.
second is unique inverse, right? Yeah, I'm writing it. I am basically going to upload this thing, so you will be having that. So something which is a concept, actually, I would tell you the reason why we have it, but let's just say about it. So we have vector space, which has all the elements which are vector and which follow the rule of vector addition and scalar multiplication. Now, what we call as the subspaces, let's say there exists within this vector space some a smaller set of vectors W. So this is a general way of saying contained in. Let's consider a set which is contained in my original vector space, such that if U and V belongs to W, implies U plus V also belongs to this, and alpha U, so alpha belonging to field, some field, alpha U also belongs to the same. If we have set of smaller set of vectors such that the addition of the vectors in that subset W results in the same W, so famous closure property, or the multiplication by scalar also results in the same W, then only these two properties, if you check it, then it will tell you whether this W is a subspace or not. So if these two properties are met, then W is a subspace. I do not need to explicitly check all the 10 properties now. I can only check these two properties and I am done. So this is the importance of the subspaces, that I do not need to check, because if I know that there is a larger vector space and I am talking about some subset which is of that larger space, I now no longer need to check all the 10 properties. If these two properties are met or verified, then you have that subspace as the linear vector space. So let's just have an example. Remember, this is an example collection of R cube where each of this belongs to this is this under the component wise addition and multiplication by a scalar, usual multiplication by a scalar, this set constitutes a linear vector space. This is what we already see. Now let me consider a set x1, x2, 1. So where you can say that the third component is always going to be 1. Or let's say another set x1, x2, 0, where the third component is always going to be 0. Does S1 constitute a vector space? Does S2 constitute a vector space? Now I do not need to check all the 10 properties. Why? Because I already know that my original S is a vector space. So I can just check the subspace properties, which are only these two, and I can say it only on the basis of that or not. So, okay, let's just question number 1. S1,
No,
is
sir.
it a subspace or not?
No, sir.
No, sir.
Why it is not a subspace?
Sir, 1 plus 1 gives 2 and that doesn't belong to the
If
S1.
we do U1 plus U2, then that can be x1 plus y1, x2 plus y2, and 1 plus 1, because each of them has this as 1. So the result comes out to be 2. So that means that x3, which is the third component, which should be equal to 1, is not going to be the case, and hence this is not a subspace or a linear vector space. Yeah. What about S2?
Yes, sir, it is.
Yes, sir, it will be.
Yes, sir,
Yes,
it will
sir.
be
Yes,
a
sir. It is.
You will see that addition of 0 will give you 0. Multiplication by any number is going to give you 0, which means S2 is a subspace. Now, please see that S2 is a subspace. It means that if you just do individually, then S2 will satisfy all the 10 properties of the linear vector space. But I do not need to explicitly check it, as I already know that the linear vector space from it is coming, that is a vector space. So that's the idea of the subspaces. Subspaces generally give you a shorthand way of figuring out whether a particular space of set under the rules of addition and scalar multiplication, whether it constitutes a linear vector space or not. Questions here?
Sir,
Hello, sir.
Yes. Yes, yes.
Sir, please check second property for S2.
For S2? Yeah.
How to check second property?
Yeah. Okay. Let me just write down. So let's just do alpha times dot u1. This is my scalar multiplication. So what will be this? So this will be alpha x1, alpha x2, alpha 0, right?
Okay.
Yeah. And this is a real number. This is a real number. This is a real number and is equal to 0, which is what the set 2 was, right?
Yes, sir.
So that means that S2 is obeying both of these properties, that if two vectors are in this space, then the corresponding vector is in the same space. So you can check it for 0 and also as for S2. And if there is any scalar, which is let's say in this field, then the corresponding one is also in the same vector subspace. So subspaces are basically a shorthand way of figuring out, but subspaces are linear vector spaces in all aspects. So I could have asked this question in other way. I could have asked this question: does S2 constitute a linear vector space? Yes, S2 constitutes a linear vector space. This is one way of saying. Another way of saying is, we know that the larger set from which S2 has come, that constitutes a vector space, and hence I can check only these two properties, and after checking these two properties I can confirm or negate whether this particular space is a subspace or not. Fine. Okay, let's do something.
Sir, I had a question.
Yes, please go ahead.
So we defined do we need to define the subspace on the same field of both W and V have to be the same field or different fields?
Good question. Actually, two things I am just going to say. Very good question. Let me just write down and then LT and linear independence. I am just going to answer that. Okay. It is implicit if we are talking about a subspace that one, the field is same over which your vector space was defined. Remember my first sentence which I wrote as that this W has to be completely contained in my original vector space. This means that it is contained in not only the field, which should be the same, real or complex, whichever was the one, but also that it is going to follow the same rules of vector addition and scalar multiplication. I cannot define new rules of the scalar multiplication and vector addition. So field is same, vector addition rule is same, scalar multiplication rule is same. All three things have to be same. And when I'm saying that W is contained, these are implicit, but yes, it's important that you remember that when we are talking about subspaces, it is over the same field, using the same rules of vector addition and using the same rules of scalar multiplication, which the original vector space was obeying. Does this answer?
Right, sir, I had a follow-up question for that. Since we define, for example, we define V on the real number. Now, if we define W on the field of W on, say, whole numbers or integers, would still satisfy those true properties. So, would that be a subspace or we
yeah, I
cannot
mean, actually, for the field, I am not going beyond right now, beyond real and the complex one. Yep.
Right, sir.
So what I want to emphasize, please understand this point clearly. When the word subspace is coming, that means that there is some original linear vector space about which you are talking about, right?
Yes, sir.
So any subspace has to be over the same field, over the same vector addition, over the same scalar multiplication. What you are defining over the different field can be a subset. But since each of that number is still going to match the same number, I mean, whatever the field is, hence it cannot go beyond it. Please understand that I cannot decide to restrict something when I'm talking about subspace. In itself, that can be a question, what you are asking. whether x1, x2, 0, that constitutes a vector space over integers under usual rule of addition and multiplication of the integers. That itself forms a question. But that won't be a subspace of something which I am talking about, where I have defined my field to be real number. When you are restricting your field also, then you are taking it to be a smaller subset of the field. But when we are talking about the subspaces, subspaces has all the property of the linear vector spaces, except that I am talking about a smaller number of vectors. In fact,
Right,
I
sir.
can also constitute my trivial vector subspaces. So for example, 0 vectors. So let me just go to this. If I have a vector space having only one vector, this, or I have a vector space which is the whole vector space itself, these two guys are the trivial subspaces. These subspaces. So I cannot decide to go out, restrict it, or expand my field. Do not have any option of doing that. When I'm talking about subspaces, in itself, you can ask that question, yes, whether this constitutes a linear vector space or not. Or otherwise, your field has to be defined in the original one. That field has to be defined. It's not a real number, it's an integer. Okay.
All right, sir.
Okay, good. Now, linear dependence or linear independence. Now, can you tell me in the three-dimensional vector space, how many directions are there? Still 5 minutes, I can go ahead. Okay, how many directions are there in the three-dimensional real vector space? Euclidean space, say famous.
3 directions.
No, I want to have 4 directions in the three-dimensional vector space. Can I have it?
No, sir.
Yes, sir.
Sir, the fourth direction can be divided into the rest 3 dimensions. So
which means that
Like linear combination.
That will not be a new direction. But what I am going to say something about the linear independence or the linear dependence of the set of vectors, that has something to do with what we call as, I mean, it gives you some idea of the direction in the three-dimensional vector space. Remember, it is difficult to think about the abstract vectors still. When I am writing, I am pretty sure that when I am writing this kind of a notation, or I am writing this kind of a notation, it is still kind of a foreign to you. What is the writing? On the other hand, if I am writing this is pretty common to you. I mean, this is what you are doing all the time. And hence my association with three-dimensional vector space helps me in remembering these concepts. So in the case of the three-dimensional vector space, we generally talk about these perpendicular directions. Yeah. So linear dependence and linear independence has something to do with that. So what it has to do with it, let's just decide it. So now I say that we have a linear vector space. So you know that we have a set of vectors over a field which follows rules. If I define my equation for any set of vectors which are lying in this vector space, u3 plus alpha n un equal to 0. So if I define an equation like this for set of vectors u1, u2, say un lying in this vector space with alpha 1, alpha 2, alpha n, nothing but these scalars, then for such an equation, if the solution is all alpha i's equal to 0, that means the only possible solution for such an equation is such that if all alpha i's are 0, then we call the set of vectors u1, u2, un to be linearly independent, Li. On the other hand, if any of the alpha I, say even one of the alpha I is not equal to 0, then that set, so if not, then that set is called to be linearly dependent. So we have a set, I mean, again, these are the set of vectors. which are following certain rules. We already know since it's a linear vector space. Now we talk about whether these vectors which we are considering, they are linearly independent or linearly dependent. I will tell you the reason why we will do that. But at this point of time, I am going to tell you further that this is going to be associated with some sort of directions in your mind. That there can be so many independent directions in a particular vector space. Now, the easiest thing is to do a problem and understand whether a particular set of vectors in a particular set of linear vector space are linear dependent or linearly independent. Let's just do that and see if we have. But before that, any questions? Okay, so let me just.
Any book suggested for doing
R.
numericals?
Shankar. R. Shankar, I mean, you do your Shom series, but R. Shankar is a book which you should use it for this one. And I mean, yeah, you are using particular book on quantum mechanics. Can you tell me?
So, R. Shankar and Jetli.
Exactly.
Jetli may or may not have that much. I mean, see, every book on, I mean, advanced quantum mechanics, the word advanced is not exactly advanced. It is beyond the undergraduate. Any book which is dealing quantum mechanics at the postgraduate level will have to have this formulation of quantum mechanics. Yeah. You can take linear algebra Shom series and you can do problems from there, because ultimately we are talking about the linear vector spaces, and that's a generalized concept in mathematics. The restrictive part of it, we are using it in our quantum mechanics. So you use Shom series book for solving problems, but then there are unsolved problems in the R. Shankar itself. You can try to solve that. If you are facing problem, come back to me. Say, sir, this question I am not even able to start. Fine. And then we will discuss that what is there that we are unable to start. Yeah. So let's consider this set. Yeah. Yeah.
Sir, is DJ Griffith any good in post
Oh yeah.
graduation?
Okay. Good book, without any doubt. DJ Griffith's first edition, if you pick first edition. So there are 3 editions to the book Griffiths. If you put first edition, then in chapter number 3, all this what we are discussing, that is given as part of the chapter itself. If you are looking at edition 2 and edition 3, then this thing has gone back into the appendices. Fine. So you can use that.
Okay, sir.
Yeah.
Okay.
Good. So yeah, please use the first edition in case if you want to. Yeah, I mean, it is there in the chapter itself. So Griffiths tried to explain it in a better way. So let's just do a set over the real numbers, that like the way I have given now the set of vectors. 3 vectors are there. Question is whether this set is a linearly independent set or a linearly dependent set. So how am I going to do it? So first, I am going to write my equation. Remember 1, 1, 1, and I should be remembering my rules in this space. Whatever the rules are, I am going to follow. Sorry. Alpha 3, 1, 0, 0 equal to my 0 vector, which is null vector is this one. So remember my rule, alpha 1, alpha 1, alpha 1 plus alpha 2, alpha 2, 0 plus alpha 3, 0, 0 is equal to 0, 0, 0. And this alpha 1 plus alpha 2, wherever you do not follow, please let me know. Alpha 1 plus alpha 2 equal to 0 and alpha 3 equal to 0. So now, what are the solutions to this particular set of 3 equations?
All 3 0 or alpha 1 equal to minus of alpha 2 and alpha 3 is 0.
All are 0.
All of
will
0.
be 0.
Oh, so alpha 3 is 0 from here.
All 3 are 0.
And then what?
Alpha 1 and alpha 2
Then alpha 1 can be minus of alpha 2.
Alpha 1 will be negative alpha.
All 3 are 0.
Hello.
No, yes, speak out.
So in the last equation, that will be alpha 1, not alpha
Yes.
3.
Alpha 1
Yeah.
will be 0.
Yeah, so this is
So that
what I want you to speak, because the last equation which I have written is wrongly written here. See, alpha 1 plus alpha 2 plus alpha 3 equal to 0. This is the first equation. Second equation, alpha 1 plus alpha 2, there is no 0. So that is 0. Third equation, alpha 1 plus 0 is equal to 0. So this is wrongly written equation. Whenever I am doing it, please correct it. And this is to see how many of you are still awake or able to follow my discussion. But anyway, now that alpha 1 is 0, is it, what are the solutions possible?
All the three being 0.
So
All
this,
three. All zero.
All of 0.
all
Linear
alpha 1
independent.
equal to 0 is 0. So this is a linearly independent set. I will end this class with questions which I want to give to you, and we will take these questions in tomorrow's class as the first thing. Fine. So let me just give you a set of questions, and then we will take these questions as this one. But any question on this linear dependence? I mean, this is rather simple one. I am pretty sure that you have done it in your BSc. So I'm not extending it beyond it. I will make some physical significance of it surely when I will come to basis. Fine. Okay. So
Okay, sir.
do this.
Sir.
So let's go to the polynomial space, and I give you three polynomials: P1t, P2t, and P3t with fixed degree, and this of course doesn't make a linear vector space. So only vector space which is possible for this one when it is degree less than equal to n. I am going to talk about only the linear vector spaces now, since I am talking about the linear independence of the vectors in this vector spaces. So let's say my P1t is t plus t square. My P2t is 1 minus 4t square plus 3t cube, and my 3t is 5 minus 2t. So I'm going to upload the notes immediately after the class, so you can actually have a look from there. Are you able to access the notes which I have just, which I actually uploaded?
Yes,
maybe
sir.
an hour?
Yes,
You are.
sir.
Very good. So I'm
Yes,
going
sir.
to upload it.
Yes,
And
yes, sir.
let me, so you please see it from there. Do not need, there is no need to write it here. But let me know whether this set of vector set is linearly dependent or set is linearly independent. Fine. You are going to use same the coefficient addition and multiplication of a scalar exactly in the manner in which we discussed. So that is the rule. Questions in today's class on whatever we have done thus far?
So,
yes.
So if we can I say that if I want to check that whether the given vector constitutes a linear vector space, then sir, I need to
check
I
all
need
the
to
10 rules.
I need to satisfy two conditions. That is vector addition, and the second one is scalar multiplication. Or
No.
do I need to do all these 10 properties that you are showing on this screen?
If a question is if a given vectors, if the given set of vector under the rule of vector addition and scalar multiplication constituting a linear vector space, then you have to check all the 10 rules. Fine, all the 10 rules. What I showed you on the subspaces was that in case if you already know that there exists a linear vector space with a larger set, so just like the way I have shown it, and I ask you if this particular vector space W constitute a subspace of the linear vector space, then in the case of the subspace you have to check only two properties. Fine.
Okay, fine, sir.
Yeah, so I can frame the same question. Let me just reiterate. I can frame the same question. So I can ask, does S1 equal to this particular set x1, x2, 1 with each of these xi is a real number, usual rule of vector addition, usual rule of scalar multiplication. Does this constitute a linear vector space? If so, you will say that, okay, it fails this property. Anyway, it is not. But I can ask this question in this. How many properties does this particular set fail? Then you'll have to go through all the 10 properties and see how many properties this guy is failing. Yeah. Or otherwise, I can ask a question like this: whether this S1 forms a subspace of a three-dimensional real vector space. In that case, you do not need to check all those 10 properties. You will say that this fails one of the property and it is failing. You understand the point? Subspaces just give you an additional idea that in case if it is smaller numbers or a smaller set, which is coming out of a big set, for which you already know whether the linear vector space concept is already checked or not, then you do not need to do further things on that. You have to check only two things. One common thing which is done, for example, let me just share with you that if we think about P infinity T as the set of polynomials with degree going up to infinity. So that means countable infinite series. So remember it is one a, so a naught plus a1t plus a2t square, and not restricting myself to tn also. It is going up to infinity. So this is you can count it, but that is going up to infinite. So if you prove that P infinite T under the rule of polynomial addition and multiplication by scalar constitute linear vector space, then P and T, which is a subset of the polynomials with degree less than equal to n. In that case, you can check whether this guy is a subspace or not. So if you already show that P infinity T is a linear vector space under the usual rule of vector addition and scalar multiplication, then for P and T, I can ask a question whether this forms a subspace of P infinity T or not, where you will be checking degree less than equal to n, just like the way it was in this, and you can just say that sir, two properties are met, and since it is subset of the original one over the same field, over the same vector addition, over the same scalar multiplication, it is going to be a subspace or in itself a vector space. You understand? It is just helping you out, figuring certain things.
Sir, one more question.
Yes.
So in subspaces, you said that if I ask how many properties are gonna be satisfied, then
all
I have
properties will be satisfied by default.
Yes, sir. If that two properties
right, if
multiplication.
those two properties are satisfied, and since it is
Yes.
coming from the larger set, then all the rest of the properties will be satisfied.
Yes, sir. So do I need to show all the properties to be
No,
satisfied, as you
that's what
said?
I'm saying. If I ask question, if this guy is a subspace of a bigger vector space, then you do not need to. If I ask a question whether this constitute a linear vector space, and you say one property is not obeyed and hence it is not a linear vector space, it is absolutely fine. If I ask you a question, if this is a linear vector space or not, and then the question goes on further, tell me all the properties which it is failing, then in that case you will have to initiate all those 10 properties and check whether it is matching or not. It's good idea to check it anyway. Okay, so let me ask, end this question session in this question. A real number, a single real number over a complex one. So let me just give you kind of set of real numbers over a complex field, set of real numbers over a real field, set of complex numbers over a complex field, set of complex numbers over a real. Will these constitute linear vector spaces under the usual rule of addition and scalar multiplication? So tomorrow, we'll do it tomorrow. Fine. We are still going to contain ourselves with linear vector spaces, so you will have all the time to ask questions anyway. Don't worry.
So that set is linearly independent.
Say it again.
That set is linearly independent, sir.
Yes,
oh, you have
sir,
already
it's
checked
coming
it.
out to be so.
Yes, sir.
Good,
Yes,
good,
sir.
good, good. So
Linear
we'll
independent.
really start it with tomorrow's class. But all of you should do it. I mean, we have a class, bigger class, right? Okay, bye, guys.
Bye, sir. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Thank you.